Hello, my name is Patrick Kajuro. Thank you for watching this video. Please Google search TIOKRS, which is the website for more materials on mathematics. Today we're going to be looking at the most basic simple rules of calculus and where it's used. So we'll begin with defining the derivative, which is to do with the rate of change. So if you have a function varying over some variable such as time, so the stock price of commodity over time, you can denote the function f of t, and you're interested to know how much does your function change with the incremental small change of time. That can be analysed with what's known as a derivative. So if we plot our graph such as this, a mathematical derivative. So there we have a function over time, f of t. As you can see, we have a function of time. This axis here is the t-axis, and this is our function. This is the ft axis, and it's varying over time. So we wish to find the rate of change at a particular point. To do that, what we are going to do is we can draw, let me draw another graph, actually, a nice one. This graph isn't that nice. I need a nice, very nice graph. Because we like nice things. So we'll do it nicely, a very nice, a highly adequate, excellent depiction of what I'm trying to get into people's mind. So we'll draw a really nice graph, something like this. That's very nice. It's very lovely. It's very nice. Here we have time, and this is our function f of t, which is varying, as you can see over t. So what we'll do is we want to find the rate of change at different times. So i.e. the rate of change means if this is a function of the price of your house over time, it goes up in June and comes down in August, goes down in September, and such like that. So that's the function of your house price over time, or function of anything over t. You want to find the rate of change. So that means if it's one day your house is worth 200,000, what will it be? What's the rate at which it will grow by the next day? So the rate of change, we draw a line 10. No, how shall we begin this? First, we'll take two values. We shall take two values. This first value, we'll call it a value at a particular time ti. It gives us a particular value which we'll denote. I'm going to write it here. FTI. Sorry, something's going on the computer. But anyway, as I was saying, not sure how visible that is. Yes. Well, here we have a value of FTI, which is the value of the function at a particular time ti. I'm not the musician. We're not interested in immature people. And here we have another value at ti plus 1. We'll denote this time value ti plus 1. So this could be time 40 seconds or whatever. This can be time 39 seconds, whatever. As long as we denote this ti plus 1 and this time ti, the value for t at ti fti and value for ti plus 1 fti plus 1. don't know how big. So this value is the function at ti plus 1, and this is the value of the function. So I'm going to cross this out because it's getting into the way. This is the value of the function fei. So now that we've done that, we can draw a line that goes through this and is tangential, sort of, to this graph. So this line here is the rate of change, i.e. the rate at which this, so the rate at which this changes is the rate at which this time changes. So if a day goes by, then whatever, a day's worth of change in the function. This can be worked out by finding this value, dividing it by this value, which can obviously be done by the following equation. I'm going to rub this out, but I'd like you to keep that in this image in mind before we can draw it. That is clearly equal to our function at fti plus 1 minus our function value at fti divided by the change in the time. Now that's very obvious. Minus ti. You might want to pause the video and think about that a bit if it's a bit too much. It's a bit too much time consumption for your mind. But that's basically how to find that slope that we saw. We draw a small sketch here, so just to remind you what it was like. Let's say something like that. Add a value here. So to find this slope here, the rate of change of the function, we take the forward value of the function at a time in the future. We subtract it from a value of the function in the past, and we divide it by the difference in time, which is very obvious why that's the case. That can be written as delta f delta t. This triangle delta means the change. So a future value minus the past value, or subtract the present value. This is what we call a derivative. So df dt, which is the rate of change, the rate at which it changes. Now, that's all nice and dandy, but the problem is, if we have a complex graph, like this, then the rate of change is varying everywhere in all directions. So we can't just take a point here and a point here and then subtract and do what we just did there. We have to do it at each individual point. What we can do to overcome this fact is we can keep this equation, and we are able to keep this equation but states that our delta t, which is this, tends to 0. And write that in a nicer form. So let me go back to the graph. We have the graph here, ft, and we have our function here. We have ti there, we have ti plus 1. So that's fine. And work that out. Here we have ti plus 1, here we have f of ti. We have in the back. Very difficult to write. So here we have the value, the value of the function at ft plus 1, and here we have the value of the function at ti. So f of ti plus 1. If we say go back to what we discussed, t equal to ti plus 1 minus ti and delta f, this is an f, ti plus 1 minus fti. So, to define the derivative, what we'll do is we will let this ti plus 1 to minus ti tend to 0, i.e. the change in time that we're looking at is so minute, never is 0, but it's very, very, very small. So this gap here, imagine this gap becoming smaller and smaller and smaller and smaller and smaller, tending to 0. So you can write that as delta t, so the triangle t tending to 0, and then write our delta f over t is equal, that's what the derivative is. That there is the definition. This is what the definition of the derivative is, nothing else. So we shall now look at derivative of some very nice simple functions, nothing complex. So that means the rate at which it changes. Remember this, making this tend to 0. Minute, small value then can work. It's a theory. In theory it should work. So we'll start off with polynomials, for those of them obviously the most simple. Say our function is function of x is a to the xn. The rate of so this is a polynomial. So it's a function of x. A is a constant. X is the variable. N is the power. So df dx, or simply f prime. This is a letter f. Remember this is letter f. Might look a bit dodgy, but that's what they look like. You take our n and you multiply it like that, and then you subtract 1 from the power. So we shall look at a very simple example. Say we have a function which is 4x cubed, and let's just add another bit to quicken this. We're going to plus, let's say, 2x. So here our a is, so our f prime, which is, we said is our derivative. So we're looking at the incremental change of this as it tends to 0. How does this function change? The f prime, so the rate of change of this function is here. 4 is our a, and obviously 3 is our n. So you keep the n comes down, so i.e. our 3 comes down. So it's 3 times 4, x to the our power 3 drops down 1, so it becomes x squared. And then for this, you've got 2 times x, so plus 2 is to the power 1, so the 1 comes down, 2 times 1, x is to the 0. X to the 0 is mainly just 1, so that vanishes. And that's the derivative of that function, 12x squared plus 2. Now we can look further at slightly more complicated derivatives. So let me just explain to you what that means. That means this function changes at the rate of the derivative which I just rubbed out. I'm sure you saw it. Now we look at rates of change of slightly more complicated functions. Let's look at some trigonometric ones, simple ones, but very, very simple. If we have f of, let's do y because that's so easy. Equal to y of x is equal to a sine x. And y prime, which we said is dy dx, or the derivative of x. So the rate of change, the rate of change means the rate at which our function y changes with a change in x. So if our original value of x is 3 and our value of y is whatever it is, then if we change x from 3 to value 4, how does our y change? That's what rate of change means, rate of change. So the rate at which our function of y changes with change in x. The derivative of that would be, let's actually make it a bit more interesting. Save time. Sine dx. So that's y of x is equal to a sine dx. This derivative is a times the derivative of what's inside here, which you should know by now is b. You should probably do some homework on that and figure it out. And then we change our sine to a cosine and keep what's inside. So with differentiating trigonometric functions, you differentiate what's inside the brackets, you multiply it on this side, you keep what's outside the bracket, and you change it from a sine to a cosine. And likewise, if you have a function of cosine, this similar method, you differentiate what's inside and multiply it by a, but you also multiply by -1, remember, for the cosine. You change it from cosine to sine, and you keep what's inside the bracket. And that's how you differentiate trigonometric functions. Find the value of the derivative at a particular point. You take the derivative and you just plug in the value of x that you're interested in at that point. Now we're going to look at slightly more complicated derivatives. We're going to look at the quotient rule. Now the quotient rule is, I always mix up what the quotient rule, how it goes. If you have a function v, some function v over what? It's never v, it's always u over v. So if you have a function that's some sort of fraction, so i.e. see 2x squared plus 3 over 4x minus 2. If you have something like that and you wish to work out the rate of change of this function, wish to work out the rate of change of this function, what we're going to do is apply this formula. So the rate of change of this function is called the quotient rule. You do, I've already forgotten actually, it's very embarrassing. It is v du dx. So you differentiate this top fraction, this numerator, by x, multiply it by v, subtract u, take the denominator, differentiate the denominator, multiply it by u, divide by v squared. So that is u, this is u, du dx is obviously, you now have to differentiate this. So u is the top, the numerator, and v is the denominator. So yes, so our derivative of u is times the 2 4x, and then our derivative of v with respect to x is 4. So now if we plug that into that, v, which is 4x minus 2, times the derivative of u, subtract. Now we're going to subtract u times the derivative of x, vx, which is 4 times u 2x cubed plus 3, and over, sorry, is it in this one? 4x plus 2 squared. And that is how to differentiate function that is of this form. I think that's going to be it for today, for this course, this teaching. Hope you learnt from it. May you please Google search TIOKRS for more in-depth detail on some of the topics in this. Thank you very much. Nice day.